Okay, so today's learning goal, we're going to start looking at we're learning to using transformations to functions to connect various representations of functions and similar functions. And so the success criteria for today is knowing the parameters of a, k, d, and c, and how they affect the base function f of x, and how we can describe that in terms of transformations. And so really what we're doing in this exercise is just investigating what these transformations look like. So I'm just going to talk through it. I'm not actually going to go to Desmos and look at it, but I'm just going to talk through what the different transformations do. So it's one thing you just have to understand is like how function notation plays a role, so that you can see where a specific type of transformation is. And so this is the warm-up question: is like what would it look like if f of x minus 3, what would f of x minus 3 look like if f of x equals 3? Or sorry, if f of x is the absolute value function. And so really what we'd actually be graphing is just absolute value of x minus 3. So that's the new input. So notice the input's being subtracted by 3. For b, the doubling is outside of the function, so the doubling shows up outside of the absolute value. The plus 3 shows up outside the function for c, so it shows up outside the absolute value. And the 3x shows up inside the function, so the multiply by 3 shows up inside the absolute value. So those are the graphs that we would actually graph. So what we're actually doing is exploring this function here with a, k, d, and c if f of x is changing. And so notice there's function notation playing around here. And so we will have f of x as the 4 different base graphs, and then look at subbing different numbers into f of x, like with a k here and a d here, and then doing things on the outside of the function with the a and the c. So in the chart, we're actually just going to rewrite the function for each of the different base graphs. What would it look like to have f of x plus 5? And so as we go, like this one's x squared plus 5, and so you'll notice that the plus 5 always shows up on the outside of the function, and the minus 6 shows on the outside of the function as well. And if you graph these, you'll notice that the parabola is just going to be shifted up 5 or down 6. The root graph will be shifted up 5 or down 6. The 1 over x graph will be shifted up 5 or down 6. And the absolute value graph is up 5 or down 6. And so this just vertically shifts the base function. If the c is greater than 0, it shifts it up. If it's less than 0, it shifts it down. For the next one, we're subbing this into the input. So we've got x minus 4 squared, square root of x minus 4, 1 over x minus 4, the absolute value of x minus 4, x plus 2, x plus 2, x plus 2, x plus 2. And so what happens here, and you might remember this from grade 10, when you graph these in Desmos, you're actually going to notice that the graph is shifting. I've always said opposite of logic, but it's really just it is actually logical. So shifting it maybe the way you wouldn't have thought it was going to go. So this is actually shifting to the right, and this is shifting to the left. One thing we say there is, like, since we're adding here, we're adding 2 to the inputs, and here we're subtracting 4 from the inputs. We actually need smaller inputs to start with. So you can imagine, like, if we're going to subtract 4, we don't want to sub in -2, -1, 0, 1, 2. We actually want to sub in numbers around 4. So like we actually want bigger numbers to start with. And so that's why it's a shift to the right 4. Here, we don't want to sub in like -2 again, because like, sorry, we do want to sub in -2, but we don't want to go all the way to +2. We want smaller numbers to start with. We want numbers like -4, -3, -2, -1, 0. Those are the nicer inputs. And that's why it's actually shifting it to the left, because you want to start with smaller x values because you're adding 2 to them. So when d, notice how it says x minus d. When d is greater than 0, so 4 is greater than 0, we're shifting to the right. But we see that as x minus d, so it does look like a minus, -4, and so you might think that's left, but it's really right. Uh, the a on the outside of the function, so what it would look like is just a 2 on the outside of every function. For the 1 over x graph, it actually could show up on the top. You can see that kind of arithmetic. This would be like 2 over 1, so that's 2 over x. And that's the only one that's kind of funny there. The 1/2, the 1/2. You can show up, this will kind of show up as a 1/2 bracket 1 over x. So it could actually show up like this, but which is a little bit confusing from the horizontal one, which we'll see in a second. But um, it is outside the function if you write it like this. And then 1/2 on the outside. And then the -3. We show that, we just kind of skip that step and just put the -3 on top. And then the -3. The negative sign can go on the front of the function or on the top. The a value can show up in the front like this, or it can show up on the top. And if you graph these in Desmos, what you'll actually notice is um, the doubling or the halving or the tripling is actually happening after you square root it, 1 over x it, or absolute value it. And so what happens is all the y values that you had before as your base graph, they're actually getting doubled or halved or tripled. So it vertically stretches or compresses, just like you've seen in grade 10 with the step pattern of parabola changing, making it skinnier, vertically stretching it or compressing it. If the absolute value of a is greater than 1, so what that means is like -3 is greater than 1 because the absolute value -3, it's a stretch. If the absolute value of a is less than 1, it's actually compression. So the 1/2 is a compression, a -1/2 would be a compression. And so what we end up doing is like multiplying all the y values by 1/2. And then if a was less than 0, so it doesn't matter, if you do get a negative sign, you have a vertical reflection. So it could open down, or the y values get multiplied by a negative. Finally, in if the multiplier is on the inside, so you're multiplying the inputs by x or by a number, you can see what it will look like. The 2x's on the inside, the 2x on the inside, the 1/2 x on the inside. So this kind of looks funny, but so you probably more see it like this as a 0.5x. The 1/2 x on the inside, -1/3 is on the inside. Again, like you could write this as a decimal, -1/3, -1/3. And so if you graph all these guys, the change here from the base graph is actually, again, opposite of probably the verticals, what you would think. And so because you're multiplying the inputs by 2, or halving them, or multiplying them by 1/3, you actually want the other way. So like imagine like it's not -2, that's the nice input, -1, 0, 1, 2. It's -1, -1/2, 0, 1/2, and 1. Because we're going to double them, we actually want them half the size that they were before. So what happens is the x's are actually going to get divided by 2, because you want them smaller because you're going to double them. And if you're going to half them, you actually want numbers that are bigger because you're going to bring them down. And so it's a horizontal compression stretch, but it is the opposite of the vertical, where like you're getting, if you have numbers that are bigger, sorry, that just popped up. If you have numbers that are between 0 and 1, you actually have a stretch. So like a 1/2 is between 0 and 1, you have a stretch. If you have numbers that are greater than 1, so if the k value is greater than 1, you have a compression. And so ignoring the negative, the absolute value should be on there. And then if you have numbers less than 0, you have a reflection. You still have a reflection like horizontally, and that's over the y-axis, so the x's get multiplied by a negative sign. And so that's how it works. So in summary, like you've got all of these letters that have roles to play in terms of transformations. The a value is vertical stretch or compression. Negatives give a reflection. The k value is a horizontal stretch or compression, but it's really like the opposite of the verticals. So if like a 2 vertically stretches, then a 2 actually horizontally compresses, and negatives give reflection. And then D, horizontal shift left or right. Um, Notice that it's actually in factored form, and we'll do more on that later. Um, and then C is a vertical shift up or down. Couple tips or tricks, like verticals are always on the outside. They happen after the function has occurred, so they actually change the y values. The horizontal transformations happen before you do the function operation, um, so they're on the inside. Um, and the stretches compressions are the only things that change the shape of the function. So shifts are kind of nice because they just move it around. Reflection's kind of nice because you've got that kind of shape, but you just have to like reflect it down or up. Um, but like stretches compressions are the only thing that actually like physically change the shape. Um, we always do the stretches, compressions, reflections first because they're like multiplication ideas, and then we can do the shifts at the end. So it's almost like a BEDMAS thing where you could, when you do your transformations, you can do your stretches, compressions first, and then always use the key points on the original function instead of trying to look at the whole thing at once. Um, and so like so take the original function and just do one step at a time. So do your horizontal stretch, then do your vertical stretch, then do your vertical reflection, then do your horizontal shift, then your vertical shift. And so just move each key point, like use the key points one at a time. So some practice, kind of just talking about like what each of these numbers are doing and describing what each of these numbers are doing. And we'll get more practice graphing them tomorrow.